Hello, welcome to this lecture. Today, first order systems. We are seeing the dynamics of first order systems. So, in this, we'll see a new topic about nonlinear system, nonlinear relationship. So, if you have a nonlinear relationship in any process, what do we do? Almost all the processes what we had discussed, if you had been following my previous lectures, whether it is thermometer or CSTR or mixing tank, or a liquid level in a tank, we had considered all of them with a linear relationship. The describing equation in these cases were linear. For example, it is CSTR, it is a first order reaction, linear relation. In thermometer, the heat transfer is HA delta T, H in the A into delta T, linear. So they're all these linear relations. With linear relations, it'll be easy to derive the transfer functions. When we have a non-linear relationship, it is difficult to derive the transfer function because this nonlinear relation cannot be Laplace transformed. So if it cannot be Laplace transformed, then it's difficult to find out the transfer function. So the transfer function helps us. It's very convenient in analyzing the dynamics of processes. It helps us to easily understand, estimate the response of processes. So this fact, the advantage of transfer function, makes us think that even with a nonlinear relationship, if we can get a transfer function by some approximation or by some modification of this nonlinear relationship, then it will be very useful. So that is what we are going to see now. We will take up the example of a tank flow of a liquid through a tank and consider a nonlinear relation for this. So this is an example of a tank through which liquid is flowing. These are the variables Q and Q naught are the volumetric flow rates, inlet and outlet. H is the liquid level height. R is a resistance. And C is a constant which we'll be using later on. Now the flow head relationship, that is the relationship between this Q naught and the head, it can have many type of relationship. So they have been discussed in detail in this my lecture earlier, titled as PC47. It can have a linear relation, non-linear relation, when it can have a linear, when it will be non-linear, some examples and all that we have discussed in this. And also for a linear relation of the form, linear means Q naught is directly proportional to H. We have taken a specific example of Q naught equal to H by R, specific example of linear relationship, and we have derived the transfer function, we have found the equation, transfer function, etc. in this lecture titled as PC48. The links for this are available in the description below as well as in the description below as well as above. Well, so if I have not gone through them, you can go through them again. So that will make you understand this lecture very clearly. Now let us take a non-linear relationship which has been described in this earlier in this, and see how do we derive the transfer function. So when you have a nonlinear equation, so let us say we have a nonlinear equation bit for the flow head. So I'm going to take a nonlinear relation, assume of the form Q naught equal to C into H power 0.5. So this is one such example of nonlinear. The flow head relationship need not all the time have a nonlinear relation by this way. It can have H power anything, H power 0.5, anything. So I am considering a simple relationship c into h power 0.5, that is q naught is proportional to root of h, and the proportionality constant c is a constant, right? The c is a constant here. So when you have this relationship, non-linear relationship, and try to proceed as before, you have the unsteady state mass balance equation for the tank explained here in this. And when we try to substitute this non-linear relation into this q naught, well, I substituted here. Proceeding afterwards will be difficult for us because this non-linear term cannot be made into a simple Laplace transform. We may not be able to transform this, and we will not be able to obtain the transfer function. So in order to make it transformable, Laplace transformable, so we need to bring this nonlinear form into a linear form. So that is what we are going to do this. How are we going to do this? We are going to do this by using a Taylor series and making some approximation. Now if you look at this equation, q naught is a function of h. Q naught is a function of h. Now if I use Taylor series to expand this function, so expand this by Taylor series around the steady state value h's, So when you do so, we get this equation. Q naught equal to Q naught h's. So this means Q naught evaluated at h's. So this means Q naught evaluated at h's. Then the first derivative, Q naught dash, this is prime is here, Q naught prime, first derivative evaluated at h's, multiplied by the deviation h minus h's. Then 1 by 2 factorial, second derivative, Q naught, Q double prime 0, second derivative of this evaluated at h's multiplied by the deviation square, and so on. This is a series, and so on. So here is what we are going to make an approximation, that we are going to neglect the h minus h's power 2 and higher orders. We are going to neglect higher orders from this square power h minus h's power 3 and so on. So all these terms from here onwards we are going to neglect, mainly because the deviation around the steady state value h minus h's is very small. That's what we're going to assume. For small deviations we can afford to ignore these terms, higher order terms, and retain only the linear portion. So if you retain only the linear portion as an approximation, this equation becomes this, and it becomes linear. It is linear. Now this nonlinear equation has been modified by this expansion and approximation into a linear form, equation number 4. So this is a linear equation. Now let us evaluate these values in this linear form. Okay, first the derivative is the first derivative, q naught dash, q naught being this, c into h power 0.5. What is the first derivative of this? 0.5 into c h power minus 0.5, is it not? So that is what, q naught dash equal to 0.5 into c h power minus 0.5. I am differentiating equation 1. I got this. Now q naught at h's, q naught dash, the first derivative, this is the first derivative. Evaluated at h's will be what? Substitute h's. So q naught h's, this term is this, equation 6. So this is equations, I can substitute for this, for this I can substitute this term. Well, now I'll substitute this in equation 4. Q naught equal to Q naught h's plus, instead of this I substituted this 0.5 chs So I substituted this 0.5 chs power minus 0.5 into h minus hs. Q naught equal to, equation 4 now becomes Q naught equal to Q naught hs plus 0.5 chs minus 0.5 into h minus hs, right? Now I will simplify this further. This Q naught hs means what? Q naught evaluated at hs. I'll simply call it as Q naught s. Okay, Q naught hs, I'll simply call it as Q naught s. And this term 0.5 chs power minus power 0.5, this I'll call it as 1 by r1. The entire term 0.5 chs power minus 0.5, I'll call it as 1 by r1. So I had used these notations in 7. Okay, Q naught hs, I call it as Q naught s, and this I call it as 1 by r1. So if 1 by r1 is this, obviously r1 I just written here as r1 also. R1 is this, 1 by r1 is this, means r1 is this. Now I'll substitute equation 8 into 2. This equation I'll substitute into equation 2. What is equation 2? Our unsteady state material balance equation. This I'll substitute for Q naught. I'll substitute for this Q naught. I'll substitute equation 8. So Q equal to, if you substitute Q equal to Q naught S plus 1 by R1 H minus Hs. After substituting this equation 8 into 2. 2 is this. This is 2. Instead of Q naught, I substituted the simple equation, equation 8. And this H minus Hs, sorry, yeah, that's right, H minus Hs plus AdS by dt. Now at steady state, we know that Qs inlet state equal to outlet flow rate. Qs is steady state inlet flow rate. This is steady state inlet flow rate. Steady state inlet flow rate equal to steady state outlet flow rate, Q naught S. So you have an unsteady state equation. This is unsteady state material balance equation, and you have steady state material balance equation. Now everything is linear. Unsteady state material balance is also linear because of our procedure. So up to this equation 8, this is a process of linearization. How a non-linearization, so how a non-linear equation, how a non-linear equation is changed into a linear equation, equation number 8. So this up to this, it is a process of linearization, right? So up to this, up to equation 8, it is a process of linearization. So now you have all linear equation as substituted. So 10 minus 11, unsteady state equation minus steady state equation, 10 minus 11. So going to give me this Q minus Qs here left hand side, and right hand side Q naught S cancels. So you have this and you have this. Now dH, I'm going to replace it as d of H minus Hs, because Hs anyway is a constant. So d into H of H minus Hs will be same as d. So after substituting these deviation variables in equation 12, it becomes this. So what is this? So this is a first order linear ordinary differential equation, right? Which can be easily made into a form of a transfer function. How? By taking Laplace transform. So if you take Laplace transform, this Q becomes Q of S, H by R1 becomes Hs by R1, and this is first derivative, right? It becomes S into Hs minus H0. Now what is this h0? So this h0 is nothing but h minus hs, h minus hs evaluated at t equal to 0. So at t equal to 0, h and hs are same. There's no change at t equal to 0. So this term is 0. H equal to hs at t equal to 0. So h0, this term becomes 0, right? Initial deviation is 0. So remaining terms you simplify. Q of s equal to, this simplification is easy to understand here. H of s taken common, 1 by r1 plus as equal to this. Take h of s common and rearrange, you get h of s by qs equal to this. R1 by AR1 s plus 1 plus R1 by tau s plus 1 equal to K by tau s plus 1, first order form. So the transfer function relating height and the inlet flow rate is the first order transfer function K by tau s plus 1, which we got it by making the nonlinear relation into relation. If I have retained this nonlinear form as such, it would not have been possible to get this first order transfer function or this transfer function. Well, now what is K? K is equal to R1 and tau equal to AR1, right? Tau equal to AR1. Tau equal to AR1. Well, that's the transfer function of this tank with a nonlinear relationship. Now coming to more important point. If you look carefully into this R1 and tau, gain and time constant, what do you see? What do you find? Okay, more specifically, if you compare these values with the transfer function of a tank with the linear relation which you have discussed earlier, what do you find? For the case of linear relation, right? A tank with linear relation where the flow head relationship is linear, like this, Q naught equal to h by r. The reference is this lecture PC48. So we had found K, that also first order, right? But gain is R and time constant is AR. So if you compare this and this, what do you find? If you compare this case and this value, what do you find? In this case, in linear relation, K is a constant and tau is also a constant for a given tank. Both are constants for a given tank here. But whereas in this case, are they constants? They depend on Hs. For a given Hs, they are constants. But for a given tank, Hs can, depending on the operating conditions, Hs can vary because the inlet, if the inlet flow rate has a different flow rate, Q or Q naught, has a different flow rate at steady state, Hs can vary. So here time constant is not a constant, is not fixed for a given tank. Similarly, the gain and time constants are not fixed for a given tank in this case, unlike where the relationship is linear. So in the case of linear, they are constants, but in this case, the time constant and the gain are variables or are varying. They may vary with the operating conditions even for a single given tank, right? So the time constant and gain are not fixed, right? They can vary. So they are variable time constant and gain in this case. So that is a point to be noted. Well, we have more such cases discussed. And we'll also have numericals to understand this better, because numericals always help you understand a theoretical question, a theoretical description. So we'll see more such things, including numericals, in these following lecture series. Please subscribe to this channel and share it to your friends, and you can follow the coming lectures. Well, see you till then. Bye.